There's a question I get asked more than almost any other. What if Einstein was wrong? What if the speed of light isn't actually a limit, just a limit we haven't beaten yet? What if an alien civilization, smart enough and old enough, found the loophole? And I want to take that question completely seriously today. Not dismiss it, not laugh at it, actually follow it through, all the way to the end, with real physics. Because when you do, when you genuinely ask what breaking the speed of light would require and what it would mean, you don't arrive at a world of easy interstellar travel. You arrive at something far more disturbing, something that makes you wonder whether the speed of light is a limitation at all, or whether it's a protection. Let's start by being honest about what the speed of light actually is, because I think a lot of people understand it as a speed record. The fastest thing we've ever measured, a kind of cosmic speed camera result that reads 186,000 miles per second. And because it sounds like a measurement, like a record, it feels like something that could be beaten. Records get broken. That's what records do. But the speed of light is not a record. It is something much more fundamental than that. It is a structural feature of the universe, woven into the mathematics of space-time at the deepest level we understand. Here is one way to see what I mean. In Einstein's special theory of relativity, the speed of light appears not as the fastest thing we've measured, but as the conversion factor between space and time. It's the number that connects the space dimension and the time dimension into a single unified space-time. It sits inside the equations not as a speed limit, but as a geometric constant. The way pi sits inside the equation for a circle. You can't make pi smaller by trying harder. You can't make the speed of light higher by building a better engine. It's not that kind of number. Now, what happens mathematically when you try to move faster than light? In special relativity, there is a quantity that all observers agree on regardless of how fast they're moving. It's called the space-time interval. It combines the spatial distance between two events and the time between those events into a single number. For events that are separated in a way that allows a signal moving at the speed of light to connect them, this interval is zero or positive. These are called time-like or light-like separations. But when you try to travel faster than light, something strange happens to this interval. It goes negative. And a negative space-time interval means the time ordering of events becomes observer-dependent. Two different observers, moving at different speeds, will disagree not just on how far apart two events are, or how much time passed between them. They will disagree on which one happened first. Cause and effect, in the wrong order, depending on who's watching. This is not a philosophy problem. It's a mathematics problem, and it has a very specific consequence. If you can send a signal faster than light, then in some reference frames, the signal arrives before it was sent. The effect precedes the cause. And if effects can precede causes, you can construct situations where the effect prevents the cause from ever happening. These are called causality paradoxes, and they're not quirky puzzles for philosophers. They are the universe's way of saying that the scenario you've proposed is internally inconsistent. A universe where faster than light travel is possible is a universe where you can send a message back in time. A universe where you can send a message back in time is a universe where you can prevent the very events that cause the message to be sent. A universe where causes can be prevented by their own effects is not a universe at all. It is a logical contradiction. So when physicists say faster than light travel is impossible, they are not saying we haven't figured out how to do it yet. They are saying that a universe in which it is possible cannot maintain a consistent timeline. It collapses into paradox. The speed of light isn't a barrier holding us back. It is a feature of reality that keeps causality intact, that keeps time pointing in one direction, that keeps the universe coherent. Now, I said I would take the question seriously, and taking it seriously means looking at the proposals that smart people have made for getting around the speed limit, because there are some real ones, published in real physics journals, written by credentialed physicists. Let me walk you through the main ones and show you what actually happens when you look at them closely. The first and most famous proposal is the Alcubierre warp drive. In 1994, A Mexican physicist named Miguel Alcubierre published a paper showing that Einstein's equations of general relativity permit a solution in which a region of space contracts in front of a spacecraft and expands behind it. The spacecraft sits inside a bubble of flat spacetime. The bubble moves. The spacecraft, relative to the spacetime inside its bubble, doesn't move at all. It just sits there while the universe rearranges itself around it. This is clever, genuinely clever, because the speed of light limit applies to objects moving through space. If space itself is moving, if the geometry is shifting, then in principle there's no speed limit on how fast the bubble can travel. The spacecraft isn't breaking the speed of light. The space-time bubble is moving, not the ship. When this paper came out, it generated enormous excitement. Finally, a physics-consistent framework for faster-than-light travel. Einstein's own equations producing a warp drive. But then people started doing the detailed calculations, and the problems emerged one after another. The first problem is energy. To create the Alcubierre warp bubble, you need to curve space-time in a very specific way. You need to compress it in front and expand it behind. The mathematics of how to do this requires a form of energy with negative energy density. Not low energy, negative energy. Energy that is less than nothing. A quantity that, if it exists in stable macroscopic form, has never been observed anywhere in nature. Early calculations suggested the amount of negative energy needed was roughly equivalent to the mass energy of the planet Jupiter, but negative. Later, more careful calculations reduced this estimate. But even the most optimistic estimates require exotic energy quantities that we have no known way to produce and no confirmed knowledge that nature permits in the required form. The second problem is control. The Alcubierre bubble, once formed, cannot be steered or stopped from inside. The spacecraft inside the bubble is causally disconnected from the front edge of the bubble. Light can't reach from inside to outside fast enough. The crew can't control the bubble's direction or send signals to influence the warp geometry. They're passengers in a box with no steering wheel. A civilization would have to set the destination before the bubble forms and have no ability to adjust course once underway. The third problem is causality, and this is the one that hits hardest. Even the Alcubierre warp drive, moving its space-time bubble faster than light, falls into the same trap as every other faster-than-light scheme. In certain reference frames, the warp bubble arrives before it departed. The causality problem doesn't go away just because you're bending space-time rather than moving through it. The mathematics of special relativity is relentless on this point. Superluminal travel, travel that is faster than light from an external observer's perspective, implies time travel. Always. Without exception. Regardless of the mechanism. Alcubierre himself acknowledged this in his paper. He noted that his solution required exotic matter that may not exist, and that it had profound implications for causality. He presented it as a mathematical curiosity, a proof that the equations permit such solutions, not as an engineering blueprint. The second major proposal involves wormholes. A wormhole is a hypothetical tunnel connecting two distant points in spacetime. You enter on one side, travel through the tunnel, and exit at a distant location, bypassing the space between them entirely. The mathematics of general relativity does permit wormhole solutions. They are real solutions to Einstein's field equations. But again, the details are brutal. A traversable wormhole, one wide enough and stable enough for anything to pass through, requires exotic matter at its throat. Ordinary matter curves spacetime inward, which would collapse the wormhole. You need matter that curves spacetime outward negative energy density again to hold the throat open. Without it, the wormhole pinches closed before anything can get through. And if you somehow manage to keep a wormhole open and use it for faster-than-light travel, you immediately create a time machine. Physicist Kip Thorne showed in 1988 that any traversable wormhole can be converted into a closed time-like curve, a path through spacetime that loops back on itself, bringing you back to your own past. Not metaphorically, literally. This is now known as the chronology protection conjecture. Stephen Hawking proposed that the laws of physics conspire to prevent the formation of closed time-like curves. That whenever you try to build a time machine from wormholes, from warp drives, from any mechanism, quantum effects arise that destroy the structure before it can function. The universe, in a sense, protects its own causality. We cannot currently prove the chronology protection conjecture from first principles, but every attempt to find a consistent physics of time travel has run into deep, unresolved problems, and there is no confirmed observation of any causality violation anywhere in the universe, despite 8 billion years of physical processes. The universe has never once produced an effect before its cause. Not a single documented instance. That is an extraordinary track record. Now, let me come back to the alien civilization at the center of this question. Let's say they found the loophole. Let's say they cracked the causality problem somehow. Let's say they have faster than light travel, and they've solved all the problems I've described. What would follow? The first thing that follows is that they can travel through time, not optionally, necessarily. Faster than light travel and time travel are the same thing, expressed differently. If they can do one, they can do the other. A civilization with FTL travel has access to its own past. It can send messages to previous versions of itself. It can change decisions that have already been made. It can prevent events that have already occurred. What does a civilization do with that power? That's a question that goes far beyond physics into the territory of philosophy and ethics. But the physics question is interesting too. A civilization that can alter its own past is a civilization that exists in a fundamentally different relationship with time than we do. The direction of causality, the arrow of time, becomes a navigable dimension rather than an irreversible flow. History becomes mutable. The timeline becomes a thing that can be edited. And here is where the physics becomes genuinely strange. In a universe where causality can run backward, the question of what caused what becomes unanswerable. Did the civilization develop FTL travel because of events in their past? Or did they reach back and arrange those events using FTL travel they developed in the future? In a universe with time travel, these questions have no stable answers. The timeline is not a chain of events. It is a tangle. Some physicists have explored the mathematics of consistent timelines, timelines where time travel is possible but where paradoxes are automatically avoided. In these models, any attempt to go back and change the past results in events that were always part of the timeline. You can't create a paradox because the universe only permits self-consistent histories. You go back, you try to prevent something, and it turns out your intervention was the very thing that caused it. This is sometimes called the Novikov self-consistency principle, and it is, at minimum, an interesting idea. But it raises its own disturbing questions. If the universe only permits self-consistent histories, then free will, in any meaningful sense, becomes very strange. Everything that happens was always going to happen. Every decision was always going to be made that way. The universe is a closed loop, not an open story. Now, there is one category of faster-than-light phenomenon that is real and confirmed. I want to mention it because people sometimes use it as evidence that FTL travel might be possible. That category is quantum entanglement. Quantum entanglement is a phenomenon where two particles become linked in such a way that measuring one instantly affects the other, no matter how far apart they are. You can separate two entangled particles by millions of miles, measure one, and the other one instantly reflects the correlated result. The correlation is instantaneous, faster than light. This is real. It has been confirmed in many experiments. It is one of the most remarkable features of quantum mechanics. But, and this is critical, it cannot be used to send information faster than light. The outcome of each individual measurement is random. You can't control what result you get when you measure your particle. You only discover the correlation after the fact by comparing results through ordinary, slower-than-light communication. The instantaneous connection exists, but it carries no controllable information. It cannot be used to send a signal. It cannot be used for communication. It cannot be used for travel. This is not a technicality. It is a fundamental feature of how quantum entanglement works. Every attempt to exploit entanglement for faster-than-light communication has failed, not because of engineering limits, but because of the fundamental randomness of quantum measurement. The universe is consistent. Entanglement doesn't break causality, because it can't be used to send a message. So where does all this leave us? The speed of light is not a wall built by a lack of ambition. It is not an engineering problem dressed up in physics language. It is a feature of the universe's deep structure, the number that unifies space and time, the constant that keeps causality intact, the boundary that separates a universe with a consistent history from a universe dissolved in paradox. An alien civilization that breaks the speed of light doesn't become a civilization of unlimited reach and power. It becomes a civilization that lives inside a causality loop, a civilization that can edit its own history, a civilization for which the concepts of past, present, and future lose their usual meaning. Whether that's better or worse than being constrained by the speed of light is genuinely hard to say. But it is categorically different from anything we mean when we talk about fast travel. I think the most honest conclusion from all of this is something I find genuinely beautiful, in the way that hard truths often are. The speed of light is not the universe's way of being cruel to curious minds. It is the universe's way of being consistent, of having a past that stays past, of having causes that precede effects, of having a timeline that is coherent rather than editable. Every time we've tested the speed of light in particle accelerators, in astronomical observations, in quantum experiments, in the GPS satellites that navigate our roads, it has held firm. Not because we haven't pushed hard enough, because it is the number the universe is built around. If aliens are out there, and I suspect they are, they live inside the same universe, the same equations, the same space-time, the same speed of light. Not because they're not smart enough to escape it, but because escaping it would mean escaping causality. And a universe without causality isn't a universe any civilization can exist inside. The speed of light is the price of admission to a coherent reality. And every civilization in this universe, however ancient, however advanced, has paid that price, including whatever is out there looking back at us from the dark. They are bound by the same light we are, and somehow I find that more comforting than frightening.